Hello, in this video I'm going to show you how to actually run the parser and build abstract syntax tree. Before we can actually do this, we need to add one last thing. We need to annotate every single rule with some distinct name. This way Antler will generate different callbacks for each one of them, and we can easily know which rule exactly matched at which point. So I will start by doing something like this. You see, we need to put this hashtag, and after this we can assign some name to this particular rule. And we need to do this for every single one of them. This should be the final result. I assigned names to every single rule. Now, if we rerun Maven, we should see a lot more methods added to our listener. Alright, I run Maven package, and now I can delete the old methods, we don't need them anymore. And I'm going to implement all the new methods. There's quite a lot of them. We will need to implement every single one of them, which is going to be a little bit tedious, but the implementations are usually short, so don't worry. Okay, before we actually go any further, let's make our abstract syntax tree. As you've seen before, we have the following statements and the following expressions. Now we would like to take all of them and for each one of them have some Java class that represents it. And now you will be able to really appreciate how much Java can help you with developing compiler. What we want to do is to create one class for these expressions, which will be named like this, one class for these expressions, which we will name like this, one class for these all expressions, which we will name as, and every one of these classes will have multiple subclasses, one subclass for each possible alternative. So it will be something like, this is the main class and has many subclasses. Similarly here, we don't need a separate subclass for this, because it doesn't add anything new. Also, take a look at this particular class, it's very interesting. You can see that all of those rules, they look basically the same. There is very little variation. The only difference is in this operator. So we can actually make them more compact in this special case. We can have only one single class, and it will just have some integer field that will tell which variant it is. So here I created arithmetic class. You can see the example. I already added two string operations to make it easy to debug later. Every one of these subclasses takes two arguments, some of them take only one. These constructors exactly correspond to the rules in the grammar, which makes it very easy to understand. The only classes that look a bit different are the variable and integer classes, which correspond to tokens from tokenizer. It just takes string and it just takes integer value. And notice the recursive nature of this data structure. Every single of these subclasses implements arithmetic expression, and it takes as an argument an arithmetic expression. That's why we don't need a separate class for brackets. Something like this, it doesn't really introduce any new functionality. It's completely unnecessary. Therefore, we can skip this altogether. Now take a look at the logical expression. This is just one class, and it has integer type, which differentiates which operation was used. There is one integer value for each possible operation. And as we create it, we just pass the type to the argument. This way, we don't need to create separate class for each one of them, because the implementation of each of these subclasses would overlap and there would be lots of code duplication. The last necessary class is statement. This one probably has the most variety of subclasses. There is one for if statement, for while statement. Notice also how the arguments exactly correspond to the definition in grammar. Here is if, it takes logical expression and it takes statements. And here it takes logical expression and it takes statements, just like in grammar. Okay, so once we've got our abstract syntax tree ready, we can start implementing these. As you probably already know, all parsers are based on stacks. And here we will actually need three stacks, one for each of the classes that we created. You can see here is one stack that contains arrays of statements. This one will correspond to this rule. Essentially, the rule statements is just a linked list, but here we will store everything in array list instead, although if you want you can use linked list. There is one stack for logic expression, and there is another for arithmetic expressions. Now the general idea is to push elements onto some of these stacks whenever we enter some token and pop whenever we exit. However, sometimes we might not want to pop at all, and sometimes we might want to pop multiple times or push. However, you should always make sure that the number of pushes must be equal to the number of pops from the stack, so that by the end, after reading the whole file, the stack should be empty. For example, as we enter the if statement, it will require two arguments. Take a look here. It requires logical expression and it requires statements. So as we enter, we need to push onto the stack a new empty list of statements that will be populated, and then as the parsing finishes, we will pop from the stack and use it to build the if statement. In particular, it will look like this. Here we add new array list of statements, and as we exit, we will pop the array list of statements. Between these two methods are called, lots of other tokens will be parsed, lots of other methods will be called, and in the meantime they will all write to this array list. So when we pop it, we will contain all of those parsed things in the middle. Then we will create a new if statement, and we will also use the logic expression that will be created in the meantime as well. While statement will look similar, now assignment will be a bit different because we do not need to collect any statements. We only need to collect arithmetic expression. So it will look like this. It will just pop arithmetic expression from the stack. It will create a new assignment and it will add it to the current list of statements. The read statement is going to be much simpler. It only takes the current ID. You can easily use context to query values of all tokens. In this case, we want to know the value of token ID. If you look at the grammar, you will see it here. This is the read rule, and this is the token that we want to query. Now, exit rule is very similar, except that we pop arithmetic expression. All the logical expressions will look like this. We pop two arithmetic expressions, and you need to pay attention to the order in which we will pop, because as the parser parses the statement, it first parses left side, pushes it onto the stack, then it parses right side and pushes it onto the stack. So as we pop, we will first pop the right side and then we will pop the left side, and we will use them to build a logical expression, and similarly for all the other expressions. Arithmetic expressions will look like this. Here we also pop two arithmetic expressions, but then we push a new one. So in the end, this stack will only decrease by 1. Now this one is very interesting. It corresponds to this rule here. As you can see, it does absolutely nothing. So we are popping one expression from the stack, and then we are immediately pushing the same expression onto the stack, so it results in no operation. So I will just add a comment here that explains it, and that's it. The multiplication operation, the division operation, here we pass, the unary minus. Here is a rule for variable. It just collects the token of ID, assigns it to a variable, and that's it. Very similar for integer. And the last rule also pass. So the compiler is almost ready. Now we just need to call it. So let's go to our main method, and we will need to replace all this code with this. Here we call the lexer, then the output of lexer is passed to the parser. Then we need to instantiate our listener, and we will push the initial array of statements so that it will be populated, and later, as the parsing finishes, we will be able to pop it, and this will be the output of our listener. So here we actually run the parsing. Then we need to make sure that all these stacks are empty by this point. If any of the stacks is not empty, then it means that there is some bug in our code and we should probably fix it. And at the end, we are going to just print the output. Because I already added everywhere those two string functions, we will be able to see nice human readable outcome. After running it, you should be able to see the following logs. It exactly tells us what was pushed and popped at which point and what was the state of each stack. And here, the last line is the output. You can notice that it looks almost the same as the initial input, so that means everything was parsed correctly. I only changed the curly braces into square brackets and the semicolons into colons. Now, in order to transpile it into C, it will actually work very similar. As you can see, the output already very much looks like C. We only need to make certain substitutions. So it's very easy, everybody can make a compiler. So that would be it for this video. In the next one I will show you how to use our abstract syntax tree to generate C code. You can find link to this code in the description. Thank you very much for watching.